So I am treating this problem as two parts. The first part is to identify the displacement at the endpoint. However, the second part is a similar problem, but my intention is to calculate the displacement at intermediate points as well. So if you look clearly into the question, both are same problems, but the displacement has to be calculated at the endpoint here. And in this problem, we have to divide the total structure into 4 parts. And at each part, I would like to know the displacement value. Even if you look at the answers, the answer at the end point is 0.04 mm. But in this case, the end answer is 0.04 mm at the each point, that is after 200 mm, the displacements are 0.01, and for the next 200 mm 0.02. Likewise, we have to identify the internal displacements as well. Okay, now I will quickly solve these two problems in a single video. Okay, now open mechanical APDL, go to file and select the title as bar problem. Okay, click OK and click on fit view. Go to preferences, structural, okay, preprocessor, element type, add. For the bar problem, you have to select the link 180 element as well. Okay, click OK. But if you look at the truss problem, spring problem, and now bar problem, for every type of structure, the selection of the element type is most important component. This only decides the degrees of freedom of the element. So here also we have a bar problem. That means we can calculate the displacement in one direction. So I am using the link 180 element. Okay, right. Now for the link 180 element, there are no real constants and we have to enter the material properties. Go to material models, structural, linear, elastic, isotropic, and enter the Young's modulus value here. The Young's modulus is 2 into 10 power 5. You can write 2 lakhs here, or you can also enter 2 into 10 power 5 as 2e5. Click OK. For the link 180 element, there is no need to enter the Poisson's ratio value. Click OK. Now go to sections, link, add the area value. So the ID is 1 and the area value is 300 mm square. Enter the area 300. Click OK. Now go to modeling, create key points in active coordinate system. Enter the value as the node number or the key point number as 1 and the values are 0, 0, 0. No need to enter the 0 values here. Click apply, and the second coordinate is at 800 mm in the downward y direction. So the second coordinate is minus 800 mm. Click OK. Now join these two key points with lines. Go to lines, straight line, and select the 2 points. Click OK. Now go to meshing, size controls, manual size, all lines. Now, in the first case, it is a single element. So, I have to enter the total number of elements as 1. But in the second case, the length is given. For every 200 element, for every 200 length, we need an element. So, in such a case, you can enter the number of divisions as 4, or you can also enter the element edge length as 200. So, that means for every 200 length, you will get an element. The same is also can be written as the number of divisions as 4. Both are same. But for a different purpose, I am writing the element edge length as 200 and go to mesh. Lines, pick all. Okay. So that the geometrical model is converted to finite element model. I would like to know whether all the elements are formed or not. Go to plot controls, numbering, and switch on element numbers. There are 4 elements. Okay. Now, after creating the model, go to solution. Analysis type, new analysis, static, click OK. Then define loads, apply structural displacement on nodes. The top point is fixed. Therefore, select particular node, click OK and arrest all degrees of freedom. Be ensured that all DOF to be highlighted. Okay? Okay. Now, go to force moment, nodes, select the bottom node, click OK. In the Y direction, the total load is 3 kilonewtons. That implies 3000. Okay? So, at this particular node, in the Fy direction, enter the value as minus 3000. Click OK. Okay? Now, after giving the boundary conditions and loads, go to solve. Solve current LS. Once the solution is done, check for results. Go to general post processor, list results, nodal solution, DOF solution, displacement, vector, sum. Click on OK. Okay, these are the results. Okay, na? Right. Now, if you observe, the maximum displacement is minus 0.4 into 10 power minus 001. This is not only the value is minus 0.4 into e to the power of minus 001, e power minus 1. That means minus 0.4 into 10 power minus 1. And the maximum displacement occurred at node 2. Okay. Now, my intention is at which point I have got the maximum displacement. On the screen, I am able to see only the element numbers, but I would like to know the node numbers. So, go to plot controls, numbering, turn off the element numbers and turn on the node numbers. These are the node numbers. So, the maximum value obtained at node 2, that is this point. And even at the intermediate points, the displacements are minus 0.1 into e to the power of minus 1, minus 0.2 into e to the power of minus 1, minus 0.3 into e to the power of minus 1. You can check all these values here. So, 0.01, 0.02, 0.03 and 0.04 at U5. That implies at the end point. Okay. Similarly, If we model the component with one single element also, the displacement is the same. That means one of the beautiness of ANSYS is after discretization, we can calculate the displacement at any intermediate point. So this is the procedure solved using FEM, and this is solved using the ANSYS. Both are same. Okay, the displacement is same, but be ensure that the node numbers and also give the values or give the units in the same format. Everything either in kilonewtons or in newtons. Similarly, the lengths, all the lengths should be given in mms or meters. So if you have taken care of the units, the element type and node numbers, everything is simple. Another beautiness of ANSYS is it follows simply a sequential structures. You no need to look for any different kind of models every time. Just follow the same structure and apply to different kinds of problems. The only difference is the corresponding element type, and based on the element type we have to enter the data. That's all. Model the component on the screen, apply the boundary conditions and loads, and check for the results. Okay, thank you.